Great. Hi, everyone. Welcome to QHACK. It's great for everyone to be here. It's a packed house. I'm very glad that people came to join us today. People actually came from many different places. I think there's someone from Japan I heard yesterday, came from Japan. Someone from Korea, yeah. We've got from South Africa a few people. We've got from the UK, from Netherlands, from different places in the US and Canada. So thanks to everyone, even people who came from just down the street. It's great to have you all here. We have a great lineup of speakers, mentors, judges, and guests taking part, as well as the great Xanadu staff for helping out with this event. I do want to start off, after acknowledging all the people who are here, I want to acknowledge someone who's not here. So for those of you who don't know, Peter Wittick is a big force in the quantum machine learning community. He is a mentor, a collaborator, a big proponent of the field. And tragically, he went missing earlier this year, and he hasn't been seen for a number of months after a climbing trip in the Himalayas. He was one of the first speakers to confirm that he was going to join us at QHACK. So I would be remiss if I didn't mention Peter's presence, his influence on the fields, and that we're sad that he's not here with us today. This is the outline of today's session. So my name is Nathan Killorn. I'm your kind of technical host here today. I'll kick off the festivities with this very, very bird's eye view of the events and of quantum machine learning as a field in general. And then we have an amazing lineup of speakers who have agreed to join us today. Seth will be giving the next talk on kind of a high-level picture of quantum machine learning. And then Maria will follow up with a kind of near-term perspective on how to use today's available hardware in practice. And then we have Gavin here joining us, who will talk about quantum gates and gradients. And I know he's quite a good expert on that stuff. And then we're going to do a little bit of a shift. This is the schedule that's printed up here, but Will has actually asked for a little bit of shift just to make the flow make a bit more sense. So I'm going to swap Will out with Josh, who is the last speaker listed here. So Josh is going to talk about Penny Lane. And the reason we're switching is because Will is going to use Penny Lane in his talk. So Will be the last speaker. And Josh will take the slot from Will. And then we have Leonardo joining us from the University of Florence. And he's going to give us some thoughts about quantum optimization in NISQ devices and different ideas related to that. And then we have a number of speakers from some of our partners in the industry. We have Thomas Alexander here from IBM. We have Chris Grenade. Is it Grenade? Great. Chris Grenade from Microsoft, and Max Henderson from Rigetti. And thanks to everyone for participating and joining us here today to talk about your various platforms as well. And then, as I mentioned, Will give us a nice, cool finishing talk on quantum game theory, which sounds exciting. I'm looking forward to seeing what you've cooked up for us.
Mostly on the flight up.
So just some kind of basic ground rules for today's morning session. The talks will be 20 minutes plus 5 minutes of questions. And I encourage you to save your questions till the end. There'll be plenty of time to answer questions. And we should go around also with a little microphone just to record the questions for posterity. So I remind you, we are videotaping the morning sessions. There was kind of an agreement when you signed up that there was going to be media during the event. But if you're uncomfortable with any of that, please let Lara know or one of us know, and we can take care of it. But we will be forming these sessions, and we do intend eventually to put them online. So it's great if we can record the questions as well. For the same reason, I prefer that if anyone needs to go to the bathroom or anything like that, to do it during the 5-minute question period rather than leaving in the middle of the talk, because the way our space is set up here, the door is right by the speakers, and it's maybe a bit distracting to see people walk in and out of the room. So please try to squeeze in during those breaks your visits to the bathroom, or if you need to grab more coffee. I do apologize about the coffee. I heard it was a bit underdone. Promise by tomorrow we should have that figured out. So yeah, the rest of the hackathon is set up such that we finish the morning session of talks at around lunchtime. Lunch will be delivered, and during lunch you're encouraged to chat, to maybe start thinking about forming teams, because right after lunch we'll start with the hackathon. So that's when people should be coalescing around their teams. Even if you haven't a project finalized yet, at least have your teams in mind. We'll do a little bit of kind of helping people find the teams if necessary at the end, and we'll give you some rules for the hackathon, but that will start around 2 o'clock this afternoon. So right now I'm just talking about what's going to happen in the morning session. This is actually our office. This is the Xanadu headquarters. We're actually building a quantum computer here on the 29th floor. So I ask you not to go to this side of the office because people are actually working down there. That's where our lab is. And we have arranged for lab tours. If people are interested, we'll have 2 today and 1 tomorrow. So you will get a chance to see the lab. We'll do it by teams. But I ask you please to not disturb anyone on that side of the office. They're working over there, and also there's kind of their lunch area is there. So please stay to this east side of the office. There's plenty of space. There's lots of different rooms for people to use. Once the talks are finished, we'll also have access to this room for a space later on. So with that in mind, I thank you for kind of paying attention to these rules. I know it's kind of boring, but we have to start off with that. I can give you now a very biased view of the field, how I see it right now. What is quantum machine learning? What does it mean to bring these two things together? So the first part is quantum, and for this I mean quantum computing. So as I said, this is going to be a very bird's eye view. So I'm relying on the other expert speakers here to give you a more in-depth treatment. I'm just going to give you the highest level picture possible. So we start off quantum computing. It is a circuits model. So there's this notion of wires and gates. And the wires are actually physical systems. And the physical systems can carry information, right? The state of a physical system can carry information. Those are the wires that we're using in our computer. And then gates are the things in a computer that you use to transform information. And the gates in quantum computing are physical operations that nature gives us at the quantum level. Right? So we have this basic notion of wires and gates. I said that we have physical systems and they carry information. Technically, this information is somehow encoded in this vector space, this very high-dimensional space that has complex numbers associated with it. Complex numbers are the thing that allows us this interference property of quantum physics. So we have, in fact, everything that happens in quantum mechanics in some sense is linear, which maybe seems boring, but it happens in a very high-dimensional space, which kind of compensates for the fact that it's linear. And you have these complex numbers which give you interference effects. And then the last kind of key point about quantum computing is that there's some advantage there. Quantum computers naturally allow you to evaluate functions which a classical computer would find hard. So if I give you infinite resources, a classical computer should be able to do anything a quantum computer should do, but you'll have to wait a very long time. You'll need tons of memory or something like that. Quantum computers let you do these things in kind of a modest amount of time. So that's the third key piece of quantum computing. It's a gate model. The information is conveyed in this complex Hilbert space, and it allows you to evaluate functions that are otherwise intractable. The other part is machine learning. I want to connect quantum computing and machine learning. And this, I'm going to focus, as I said, I'm biased. I'm going to focus on deep learning here. So the first kind of concept you get from machine learning is you're a programmer, but you don't program your entire program at once. You program part of it. You say, here's the scaffold of what I want my program to do. And you leave a lot of things flexible. You say, I'm building a car. Here's what the car looks like, but I don't care where the doors go. I don't care what color paint it is. I don't care about the windshield. That's all going to be kind of determined later. So in machine learning, you have this idea of programming first starts with building a model, making an architecture, and then later on you're going to do something with it. Another part that I think is important is actually tracking how information flows through your system. And the reason I'm bringing this up is because I want to draw analogs to quantum computing. So in deep learning, at least, the modern software libraries actually track every single step of the computation. And they track the dependencies between different steps. And you can start linking them together in this graph-like structure. And that tells you how the data flows through various steps in your computation. Another really important thing, especially in deep learning, is that every step in this data flow graph, every step in this computation has this smoothness property. It says that I know if I perturb the system a little bit, I can kind of predict how it changes. So I'm able to kind of foresee how small changes affect the final result of what my computation does. This is really important. And this is something that's sometimes called differentiable programming. And then kind of putting it all together, we built the model, we represent it as this data flow graph, and we recognize that this data flow graph is differentiable. Each step is predictable, and I can kind of track from the input how a change in input changes the output. The final step is saying, well, since I know how to change the output given the input, I can actually figure out ways to push the output towards where I want it to be, right? And how I decide where I want it to be is by looking at data. I take data and I use it as a reference for how I want my model to behave. Right? So this is the notion of training the model. I first built the model, which is more just like a scaffold with a lot of free parameters in it. And then I use data and in this property of differentiability to steer it towards the version of the model that's somehow best fits the task at hand, which is defined by the data that I use. Okay. So I went through quantum computing. I went through a very biased take on machine learning. And now I'm going to say, how do those things work together? How does that give us quantum machine learning? So I'm going to repeat the same talking points I had in the previous slide. So now, with a quantum machine learning, the notion of building the model means that I specify a particular quantum circuit. I say, here are the wires, here are the gates in my quantum circuit, here are the free parameters. And this is called a circuit ansatz sometimes, and ansatz basically stands for educated guess, right? I build in some sort of implicit structure that I'm assuming about my computation, but it's not so inflexible that I can't adjust later on. So I leave some of the parameters free. And these parameters are the parameters of the actual gate. So if my gates are doing an operation like a rotation of a qubit, maybe the amount of rotation that I do is not fixed. I leave that as a variable. And then I made this analogy earlier of this data flow graph. It looks kind of like a circuit. So I want to combine these two ideas together. The quantum gates model itself, this notion of these wires with gates acting on them, that itself is a data flow graph. You can kind of track the information flow from the start to the end, and every gate is transforming that data in some way. It does something a little bit differently than in classical computing because you have quantum features at play like entanglement. So you're actually able to entangle different wires, which is not something that you can necessarily do in a classical model. But still, the idea of this being able to track every step of the computation along this data flow graph, it still holds if I'm using a quantum circuit. I want to combine the ideas of differentiable programming and this vector space, this Hilbert space idea. So linear algebra is the basis of vector spaces, and linear algebraic operations actually are differentiable as well. So I can predict how the output changes when I apply one of these linear algebra transformations. So this differentiable programming idea that I said, I want to be able to predict the output given the input, this applies also for quantum circuits. And then train the model. So in the case of quantum machine learning, train the model means I can actually take all of the ideas that are already available in the machine learning literature and use those same ideas to train a quantum computing circuit in exactly the same way as I would train a machine learning model. You can port pretty much all of these ideas in some way to be quantum aware, which allows us to leverage basically all the tools that are already developed over years for machine learning and now apply them specifically to quantum circuits, which we treat as just another kind of machine learning model. And then advantage. So I mentioned that quantum circuits have this property that they can evaluate functions that are hard for a classical computer to evaluate. So that means if I'm able to train a quantum circuit, some of the targets that I could hit with my training procedure are going to be these intractable functions. I have this bigger space of functions to play with that have some sort of advantage in my machine learning family that I'm able to train over. So there's some hope that by training I can find those exceptional spots where those functions are doing something quite interesting. So as I said, that's a very, very, very high level view of the field, and I'm going to get the other speakers to give you a more in-depth treatment. Now I just want to give you just a little bit of inspiration for the hackathon, if I may. So this slide says dream big, right? We're at a hackathon. It's cool to have like your flashiest ideas, your funnest ideas. Anything goes here, as long as it's within the scope of quantum machine learning. Then any cool idea you have is viable. But don't dismiss the simple ideas. That's what I want to point out here. Sometimes the simplest ideas are the ones that are hardest to find. In retrospect, they may seem super easy, but sometimes they're not obvious at the start. So don't dismiss simple ideas. So I want to give you a couple examples here. The notion of computer games, right? So back in the 1950s, 1960s or something, they had these gigantic mainframe computers. They were meant for computing like logarithms or computing like in the Manhattan Project, you want to compute some cross-section of some model that you're working on. Really boring scientific things. Computers were designed for hard computational tasks. And then some hackers, some goofballs in their dorm room or whatever, they were like, you know what, I want to do something really stupid here. I want to code a game onto this mainframe computer, right? I want to fight aliens. I want to fly a spaceship, right? Nowadays, computer games are a huge, huge industry. I think there's even this esports phenomenon where we have people attending like stadium events, watching other people play video games, right? So it seems really, really obvious in retrospect that of course you can play games on a computer, right? But at some point it wasn't so obvious. And I want you to think these same things for quantum computing. Maybe in the future there's something that'll be super obvious for people, but right now it's not so obvious. And maybe in this hackathon you'll find that idea, right? You'll make that connection. Another idea, this is something that's completely ubiquitous, web pages, right? Everyone uses the web. We don't even think about it anymore. But at some point, some guy was sitting in his office, and he was like, yeah, we use this internet to send emails to each other. We use it to share files and to log onto remote servers. But what if there was like just a static object you could go and like see things, right? Like instead of TV sharing something with you, I can choose when I go and look at something, right? And then on top of that, let's actually make those things connect to each other. Let's have this like implicit idea where I click a button and it knows that I want to go to a different place. And I can kind of jump around in this ecosystem of web pages. Again, something that's super, super simple, super ubiquitous in everyday life, but at some point it wasn't so obvious, right? Someone had to make that tiny little leap of intuition, come up with this very simple idea, and it has huge outsized effects. Finally, this one's maybe slightly different. Electricity is obviously something that led to an industrial revolution when people suddenly were able to connect their homes to power lines and light up their homes. So before they're burning candles, they had whale oil or something weird like that. And suddenly there was this idea of light bulbs, right? I could light my home. I don't want to talk about light bulbs. I want to talk about light bulb sockets, right? So when light bulbs were first invented, you had these sockets where you screwed them in, very similar to what we have today. And at some point, some genius or some grunt, I don't know who it was, but someone had the idea like, you know what, we can use electricity for other things, right? We can have home appliances. We can have other things that we use at our home that rely on electricity. But in those early days, that was such kind of a different idea that they still had to screw those things into the light bulb socket. There was no notion of a power plug where you could put a universal kind of medium, anything could go into that. There was only light bulb sockets. So electricity was designed around light bulbs. And then only later on did someone realize like, oh, I can graft this other thing through that and it works perfectly. I could have a washing machine now, right? These are, again, really simple ideas, really obvious now, but at the time they require a little bit of a leap. So I encourage you to think the same way today. So some final words of advice for the hackathon. Number one, this is actually a unique opportunity. So this was an invite-only event, so you guys are kind of lucky to be here. This is a cool thing to take part in. But I actually want to say, like, the idea of a quantum computing hackathon, this is also very new. When I was a grad student, I remember we were trying to find ways to generate more engagement around quantum computing. This is maybe 10 years ago. And someone had the idea, they said, oh, you know what? In the computer science community, in the programming community, they have this idea of hackathons, right? Where people get together, they have fun, they do something cool. Why don't we have like a physics-a-thon, right? Let's do a physics-a-thon. The name never caught on, And at the time, it didn't seem like a great idea because there wasn't a lot you could do. Like, what would a physics-a-thon be, right? We get together, we write equations on the board, right? No, so a hackathon somehow has this notion of programming of computers, right? It's more accessible. This is a unique thing. This is new, the availability of quantum computing hardware for the everyman, the ability to connect to these devices. And you'll be able to connect to those devices through this event. So take this opportunity for what it is. It is quite unique. It's a new time. We're kind of changing. We're shifting the ways of the field. So this is exciting time to be part of the community. It is still early, though. So I warn you, like, you will be frustrated. These devices are small. They are noisy. You will not be able to do the amazing things you're dreaming of doing. That's OK. That'll happen. But sometimes creativity comes up under constraints. When you're forced to work around the constraints that reality gives you, that's when inspiration can strike. That's when you can find the smart way to do things. Somehow, if you had unlimited resources, your creativity might suffer. So you will struggle with reality here, but take it as a benefit rather than a drawback. Third, have fun. It's the point of the hackathon. Have fun, hack away, chat with everyone else, enjoy yourselves. We got lots of games and toys and stuff, so feel free to use any of them. That's what they're for. Enjoy yourself. We'll have a social event tonight. We also had a social event last night. We had a great turnout, so I encourage you to really enjoy yourselves during this. And then the final point. Oh, I've screwed it up, but I was supposed to say C number 3. Have fun. It's redundant. C number 4, C number 4, C number 4. That's it. Thank you, everyone. Welcome to QHACK.